having calculated the electric field of an infinite non-conducting plane of charge, then we can find the electric field when we have two identical infinite non-conducting plane. One is positively charged and the other is negatively charged, given that the charge density on each of them as a magnitude is the same. So this is a look at these two planes from the side. This is the infinite positively charged plane. This is the infinite negatively charged plane. The charge density here, I call it sigma plus. The charge density here is equal to sigma minus. Now, sigma plus, my assumption is that sigma plus is equal to sigma minus, and I call it sigma. Okay, so the magnitude of the charge density is the same. Now, I want to find what is the electric field throughout the whole space when I bring these two infinite planes together. So I have two regions in space, three regions of space. I have region 1, I have region 2, and I have region 3. So I want to find what is the electric field in region 1, what's the electric field in region 2, and what's the electric field in region 3. Now, Gauss law can be applied to this situation from scratch, but with the knowledge of the electric field of an infinite sheet or infinite plane, the wisest approach actually is to use that knowledge and apply superposition. And it will be a good example also of how to apply superposition even when you have charge distributions which are not point charges. Now, in this case, our charge distribution is a continuous charge distribution. So let me consider first region 1, for example, here. I want to find what is the field in region 1. Let me remove this here, keep it in mind. So in this region, what is the electric field here? Now, superposition says that the electric field here is found, can be found by first finding the electric field due to the positive sheet, assuming the negative doesn't exist, and then finding the electric field of the negative sheet, assuming the positive one doesn't exist, and then adding them vectorially. This is what superposition principle is about. So let's proceed. We know what is the electric field. So let me, I know that the electric field, of course, I know that E plus is equal sigma plus over 2 epsilon naught, and I know that E minus is equal sigma minus over 2 epsilon. You can put here also magnitude, although this is positive. Okay, what does this mean? They mean that the electric field due to the positively charged sheet on the right or on the left is just as a magnitude is the charge density divided by 2 epsilon naught. This is the result from our example of a single infinite sheet of charge. Now, and it is directed, it's away from the positive charge on both sides, it's symmetric on both sides, and directed away from the charge, and it is independent, it's uniform. Now, for sigma minus, the only thing that changed, as I have mentioned when I discussed that example, the example of a single sheet of charge, is that the field will have the same magnitude, but the direction will be towards the plane of charge, okay, towards the plane of charge. Therefore, at this point, I can draw what is E plus. This is E plus, which is the electric field due to the positively charged plane. And this will be E minus. Assuming the absence of E plus, you just draw E minus. Why E minus? Because E minus, the electric field of a negatively charged plane, is directed towards the plane itself. Okay? So the electric field in region 1 is equal E plus plus E minus. Now, evidently from here and from this result, E minus is equal minus E plus vector, because it's equal magnitude in the opposite direction. So this is equal E plus minus E minus, where the magnitude of E plus is this, the magnitude of, and which is equal to the magnitude of E minus. Given, of course, that what? Under what condition? Under the condition that sigma plus equals sigma minus. Okay? And so this gives you 0. Now, it is evident that you can repeat the same argument for points in region 3. In region 3 here, this will be the direction of E plus, and this will be the direction of E minus. And again, E plus and E minus are equal in magnitude, given the sigma plus is equal to sigma minus as a magnitude, and their sum will also give 0. And so I can also immediately write that E3 is equal to 0. So I have no field in this region, I have no field in this region. What about the field in between? Well, probably you have guessed now that here the field will build up rather than cancel each other, or the two fields will build up. So if you consider this point, which is true, you consider this point, then I have, or let me put it here in the middle, somewhere here. This is point, the choice of this point is arbitrary, because you know the fields due to each of these, E plus or E minus, is uniform. So it's the same wherever you choose the point P. So E plus is in this direction, and also E minus now is in the same direction, because E plus is directed away from the charge, the charge plane. E minus in this case is directed towards the plane. So this is what you have, and therefore if you write E2, it will be E plus plus again E minus, and E minus in this case, in this particular case, E minus is equal to E plus, not minus E plus. So this will be equal to twice E plus. Okay? And what is the magnitude of E plus? I know that E plus is equal sigma plus over 2 epsilon naught, which is equal sigma over 2 epsilon naught, because you know sigma plus equals sigma minus equal. And so E 2 is equal, as a modulus, E2 is equal twice this, so it's equal sigma over epsilon naught. Now, sigma here is the charge density on any of these planes, the absolute value of the charge density on any of these planes, because it's the same. Okay? So this is twice the field of a single plane, okay? Which we expect. So therefore, in this region between the two plates, we have a uniform electric field, and whose magnitude is given by sigma over epsilon naught.